A warm welcome to all the students. In this lecture, we are going to solve yet more examples on non-deterministic PDA that we started in the previous lecture. Now here, we are asked to design a NPDA for the language L equal to a raised to I, b raised to j, c raised to k, such that I, j, k, three parameters, all of them are either greater than or equal to 0, and I is nothing but j plus k. Now looking at the given problem, okay, what do we analyze? Let's see. The very first thing is, what is I? I is nothing but it is sum of j and k. Okay, so substituting I equal to j plus k, the given language can be rewritten as the given language can be rewritten as L equal to a raised to, what I'll do is I'll substitute I with j plus k, so a raised to j plus k, b raised to j, c raised to k, such that now since I has been vanished, so I don't have to write about I will just say j and k is greater than or equal to 0. Okay, so this is what we get. So the language can be written like this. Okay, now why I have not written this I? Because in this expression here I has been vanished. I has been already substituted with j and k. So I say j and k should be greater than or equal to 0. Okay, so now we have to take up this language and we have to try to simplify it further and design a PDA for this. Okay, so I will just call this as language 1. Now we have a raised to j plus k. Now this can be further written as, okay, I will say 1 can be further simplified as L equal to a raised to j, a raised to k, b raised to j, c raised to k, such that j and k can be either greater than or equal to 0. Okay, now you see a raised to j is there, b raised to j is there, a raised to k, c raised to k. So I will just just shuffle their order without affecting the expression. What I will do is I will just shuffle the order. So this can be further written as, I will just move this a raised to j inside and a raised to k out. Okay, so I will do the changes here. So a raised to k outside, a raised to j inside. So now we have this particular language, okay, and this is the final simplified version, and your PDA you have to design for this language. Now what can you observe here? So one thing is very simple. Okay, even in this you could have easily observed that total number of A's, which is equal to I, okay, total number of A's is the sum of total B's and total C's. So suppose there are 3 B's and suppose there are suppose there are 3 B's and suppose there are 3 C's. So 3 plus 3, so A will be how many? 6 A's. So total number of A's is basically the sum of total number of B's and total number of C's. Okay, so we observe that, okay, total number of A's equal to the total B's plus total C's. Let's take an example. What kind of strings do we get in this cases? Okay, suppose I say k is 1. Okay, let k is 1, and let's say and j is say 2. Okay, then a raised to k, a raised to j, b raised to j, c raised to k can be further written as, I am just substituting the values of k and j. So this will be a raised to 1, a raised to 2, b raised to 2, c raised to 1. Okay, so wherever there is k, I have substituted it with 1. Wherever there is j, I have substituted that with 2. Okay, so the string that we get in this case of mine is 3 A's followed with 2 B's and 1 C. So looking at this, okay, you can easily make out, okay, that the string is valid if the total number of A's, okay, should be equal to the sum of total number of B's and total number of C's. Now, how are you going to design a PDA? A very simple thing. Suppose this is your stack, okay, Z0 initially is present in that. I will use this approach. Okay, no matter how many A's are encountered first, okay, see, order of A's is there. Only after all the A's are exhausted, then B's will start, and only after all B's are exhausted, then C's will start. Okay, so order is important. So what I will do, initially when the first A is encountered, I am going to push that A onto the stack. Okay, now when the second A is encountered, that A also I will push onto the stack. Basically any number of A's that I encountered, okay, all of them will be pushed onto the stack. So there are 3 A's in the string, given string, so all 3 A's are pushed onto the stack. Now when the first B is encountered, okay, what I need to do is, I need to check, okay, if there is a matching A on top of the stack. When the first B is encountered, if there is a matching A on top of a stack, okay, then B will be cancelled with A. Okay, that means the current B will be cancelled with the A that was inserted last, which is actually the topmost element. And cancelling means what? Cancelling means popping that A out of the stack. Okay, and the pointer will move to the next B. Then again, if there is a B encountered, which is a current input symbol, okay, you check who is there on top of the stack. There is still A, so B and A will cancel themselves. Okay, now basically this A is supposedly this A. This A is actually this A. Okay, so the current B and that A will be cancelled. That means A will be popped out of the stack, and the pointer will be incremented by 1. Pointer will be incremented by 1. Now all B's and all A's are cancelled. Whichever are equal number of A's and B's, they are cancelled. Now the remaining A's which are left should be cancelled with the remaining C's. Okay, so when C is the next current input symbol, I check on top of the stack, there is a, so I cancel that C, I cancel that C with that A, okay, which is actually the topmost element. Okay, so after doing this, what will happen? The pointer will still increment itself by 1. So now what has happened is, when there is nothing remaining to be read, that means when null is read, stack has turned out to be empty. That means every A has been cancelled with either a B or a C. So finally the string wherein every A has been cancelled with B or a C, and there is no A that is left to be cancelled, or there is no B that is left to be cancelled, there is no C left to be cancelled. Okay, okay, such string should be accepted. Fine. So whatever I said, okay, I will quickly now draw a PDA. Okay, so a valid string, one of the valid string here is say 3 A's, 2 B's and a C. Okay, so let's start with the PDA. Initially I am in Q0 state. So what did I say? In Q0 state, when the first A is encountered, what I do? That time the stack will be empty, so I simply push that A onto the stack. This is for the first A. Now any more number of A's that I encountered, okay, I will simply push those A's also onto the stack. Okay, so when the first A is encountered, stack will be empty. That A I am going to push onto the stack. When the second, third, fourth A's are encountered, there will be A already present on top of the stack. So when second A is encountered and A on top of a stack, what I will do, I will push this A also onto the stack. So this process will repeat for all possible A's, no matter how many A's are there. For every A, PDA is going to execute these transitions and it is going to remain in Q0. Visually, all the A's will be pushed onto the stack and the state will be Q0 only, right? So what has happened is the first A, okay, the second A and the third A are already pushed onto the stack. Okay, now when the first B is encountered in Q0 state, okay, in this Q0 state, when the first B is encountered, okay, PDA is going to check whether A is there on top of the stack, right? If A is not on top of the stack when the first B is encountered, it means somebody has given you string wherein it starts with B. Understood? Suppose here, okay, you observe that there is no A on top of the stack. Suppose stack is null. That means there were no A's before B's, right? So such string should be rejected. So those transitions I will not write. So when the first B is encountered and at that time A is on top of the stack, then what I do? I match and cancel that B with the A. So I pop A out and I will push null inside. Okay. So graphically what I have done, see, I was in Q0 state initially. First A was pushed onto the stack, second A was pushed onto the stack, third A was also pushed onto the stack. This was the string. Now when the first B is encountered, we checked A on top of the stack. Okay, so if B is the current input symbol, A is on top of the stack, I pop that A out. That means I cancel the B with the previous A. So I pop that A out. That's the meaning of it, right? And the pointer moves to the next B. Correct? And by doing this, from Q0, you move to which state? You move to, let's say, Q1 state. So when the first B is encountered, and suppose A matching A is there on top of stack, I cancel it. Okay, cancellation happens, matching happens, and by doing that, I go to Q1 state. Now it can so happen that there might be more B's. So like when we increment the pointer, okay, in Q1 state, now you encounter another B as a current input symbol. That time also you check whether there is a matching A on top of a stack. If yes, then that B will be cancelled with that A. So that means the B will be cancelled with A. So the topmost A will be popped out of the stack. Okay, so topmost A will be popped out of the stack and the pointer is going to increment to the next element. Okay, now in this example there were only two B's, but there it can be a case that number of A's and number of B's could be more. Okay, so here from Q0 you make transition to Q1 when you encounter the first B. Now if there are any more B's, okay, that are read, that time A will be on top of the stack. So you do the same thing, you go on cancelling each B with A and so on. Okay, now so in Q1 state, okay, when you are going to transit from Q1 state, one thing you are going to ensure that so far total number of A's and total number of B's which have been cancelled are equal. Okay, now what has happened? You are in Q1 state. Now when first C is read, what you will do? You will do the same operation. In Q1 state, when C is read, you will check whether A is on top of the stack, and if yes, that C will be cancelled with the A and you will move to Q2 state. Okay, so C you are going to cancel with A. Okay, that means this A will be popped. Okay, that means A will be popped out of the stack. Fine, A will be popped out of the stack and you will move to say Q2 state and the pointer is going to move one place to the right. Now in this example there was only one C, but there could be more C's also, right? So when you are in Q2, you are going to perform the same operations for other C's that I encountered if the string was different. So any more C's encountered and suppose top of the stack still contains A's, you are going to match them and cancel out them. That means A which is topmost will be popped out. So any more number of C's, you are going to do the same thing. Finally, Okay, when there is nothing remaining to be read, stack also turns out to be empty. What it means? It means so far total number of A's that are cancelled are equal to the total number of B's cancelled plus total number of C's cancelled. So there should not be any more A's, B's, C's left. Okay, so when there is nothing remaining to be read, stack is also empty. That time you will perform no change operation. Z0 which was on top of the stack, Z0 still remains on top of the stack, and you are going to say Q3 state, and I will call Q3 state as the final state. Fine. So this is a push down automata that we get assuming that J and K are greater than 0, right? But now your J and K can be also equal to 0, right? So there arise three cases. When J is 0 and K is also 0, then okay, the string, that is A raised to K, A raised to J, B raised to J, C raised to K, okay, will be null. That means null string should be also accepted. Okay, so from Q0, when nothing is remaining to be read, that means when null is read, from Q0 when null is read and stack is also empty, perform no change operation and you should be able to reach Q3. Okay, so this is for accepting null string, right? So this is one case. Now in the second case, okay, J can be 0 and K not equal to 0. That's case 2. And case 3 could be J is not 0 and K is 0. So both these cases also are valid. So let's assume that J is 0 here and K is 2. So if J is 0, K is 2, then the string, valid string will be A raised to 2, A raised to 0, B raised to 0 and C raised to 2. So ultimately we will get strings like A's and C's, A's and C's, and there are no B's. Okay. So these kind of strings should be also accepted. Okay, so what is this string? This is a string wherein total number of A's should be equal to the total number of C's. So in such cases what you will do? You will the first step is same. In Q0 state, no matter how many A's are encountered, just go on pushing A's onto the stack. Okay. So in my case, in case number 2, what I will do? The first A that is encountered, I will push onto the stack. Okay. The first A that is encountered, I am pushing on to the stack. Then the second A that is encountered, that also I will push onto the stack. So 2 A's are already pushed onto the stack. Then you will not encounter B, but you will encounter C. So when the first C is encountered, what you will do? You will cancel out that C with the previous A. So that means the topmost A will be popped out. The topmost A will be popped out. Similarly, when the next C is encountered, that time again you are going to check who is there on top of the stack. If it is A, okay, that A will be cancelled with C. So this C you are going to cancel with this A. That means A is going to be popped out. A is going to be popped out of the stack. Okay, and pointer is going to increment itself. Fine. So finally, when there is nothing remaining to be read, stack is also empty, the string should be accepted. So in this case 2, that is where J is 0 and K is not equal to 0, okay, you have to first push all the A's onto the stack. Now there are no B's. So what you will do? You will have a transition here. From here, you say when the first C is encountered, so you will say, I will just change the color so that this is the transition. When the first C is encountered, and suppose top of the stack is A, you cancel out the C with A and you go to Q2. Any more C's that are encountered, if topmost element is A, you cancel all those C's with all the A's. And finally, if there is nothing remaining to be read, stack is also empty, that means equal number of A's and C's have been cancelled. So you go to Q3. So this transition, okay, which in red color which I have done, this is for the case wherein j is 0 and k is not 0. Okay, now let's see the third transition, case 3. Now in case 3, it can so happen that j is not 0 whereas k is 0. So for an example, let's say k is 0 and let's say j is 2. So now the string will be of the type a raised to 0, a raised to 2, b raised to 2 and c raised to 0. So the valid strings in this case will be a's and b's. Whatever I did for c's, whatever I did for case 2, the same thing I will have to do for case 3. This kind of strings tells you that there are no c's, there are only a's and there are only b's. So you will repeat the same procedure. All the a's you are going to push onto the stack, you remain in q0. Now when the first b is encountered here, when the first b is encountered, cancel it with a, you go to q1. Any more b's that I encountered, you cancel it with a and remain in the same state q1. Finally what will happen? Each a will have been cancelled with each b. So when there is nothing remaining to be read after cancellation, okay, so I say after cancellation of every a with every b, finally when there is nothing remaining to be read, stack is also empty, you perform no change operation and you go to q3. So this is when, when k is 0 and j is not 0. Fine. So these extra transitions that I had to draw, it is only because the problem here said that j and k, it can be either higher than 0 or it could be also 0. Okay. So this is the required PDA that we get. Okay. Also in the previous lecture, okay, if you have a doubt regarding what is non-deterministic, okay, I will just show you, okay, what is the meaning of non-deterministic PDA. Okay, see the PDA and somewhere here, okay, you have a transition where on reading a and when the stack is empty, you push that a onto the stack. Now from that same state q, there is another transition defined on reading a and if b is on top of stack, then you pop it out and so on. Okay, now this PDA will be non-deterministic because, okay, from the same state, on reading the same input symbol, it is making more than one transitions. Now what is the topmost element of the stack? Is it same and all? That is not relevant. Okay, what should be relevant? From a particular state, on reading the same input symbol, you should, if you are going to more than one states, if more than one transitions happen, then it is non-deterministic PDA. Okay, so it does not mean that both these elements should be same. Only the input symbol if it's same, irrespective of what is the topmost element of the stack. Okay, if only the input symbol is same and state is same and it is making more than one transition, then you can say that PDA is non-deterministic. Now in this problem, okay, the NPDA that we are supposed to design is for the language L equal to a raised to I, b raised to j, c raised to k. Here it is given that I, j and k all are greater than 0, so null string won't be a part of it. And this is very important, either I should be equal to j or I should be equal to k. Okay, so now there are two cases. Okay, when we see the solution to this, case 1, okay, if I is equal to j, then, okay, so the string will be a raised to I, b raised to I. Why I? Because I is equal to j. So wherever there is j, I am just substituting it with I. So it is a raised to I, b raised to I and c raised to k. Correct? What I have done for case 1, when I equal to j, wherever I is there, okay, wherever j is there, I have done it ulta, but that's okay. Wherever there is j, I have just substituted j with I. So when I and j are same, that means when I is equal to j, in the string, okay, total number of a's will be equal to total number of b's. Whereas what about total number of C's? Okay, of course, total number of C's cannot be 0 because K is greater than 0. So K can be any value. Okay, so we can just ignore the value of K. One example of this string would be something like AA, B, B, C, C, C. Okay, now if you see here, A raised to I, so there are I's 2, B raised to J, so J is also 2. Okay, so there are exactly 2 A's, there are exactly 2 B's, and we are not bothered about how many C's are there. So what we will do, we will only focus, in case 1, we will only focus to see that number of A's and number of B's are equal, and then whatever extra C's which are there, we are just going to ignore them, consider and ignore them. Okay, so in case 1, if we are able to see that A's are equal to B's irrespective of how many C's are there, okay, such string should be accepted. Wherever A's are equal to B's, such string should be accepted. Now number of C's, it cannot be 0 because K also is greater than 0. But you can have 1C, 2C and number of C's. We are not bothered. No matter how many C's are there, we are ignoring that. Now, case 2 is the one if I is equal to K. Now, if I is equal to K, what I will do, wherever there is I will substitute it with K. So, A raised to K, so I am replacing I with K, B raised to J, and C also raised to K. Okay, so here A's and C's should be equal, no matter how many B's are there, we can ignore B's, right? A valid string here could be 2 A's, single B and 2 C's. Okay, so we are going to now design a PDA for both the cases. Now let's consider case number 1. Okay, it's very simple. No matter how many A's are encountered, I am just going to push all the A's onto the stack. When the first B is encountered, I am going to cancel that B with the previous A. Any more B's are encountered, I will try to cancel each B with each A which is present in the stack. And finally, when all B's are also exhausted, when I move to C, what I will do? Obviously, the stack at that time would be empty because equal number of A's and B's would have been cancelled by that time. So when C is encountered, that time definitely the stack will be empty. Okay, so all those C's which are there, I am just going to ignore them, and till we are going to do this till the string is over, and when there is nothing remaining to be read, stack also is empty, we will say that the string is accepted. Okay, so for case 1, this is the PDA. So initially we are in Q0 state. Okay, this is the initial stack. Say Z0 is the topmost element of the stack initially, and the string that we have is say 2 A's, 2 B's and single C. We are bothered about A's and B's, we are not bothered about how many C's are there. Okay, now in Q0, when very first A is encountered, when A is encountered, first A in Q0 state, I will push that A onto the stack and I will remain in Q0 state. So when the first A is encountered and that time stack is empty, I will push that A onto the stack, remain in Q0 state. So here A will be pushed onto the stack, A will be pushed onto the stack, and the pointer will move to the next element. Suppose next element is also A, then this A in Q0 state, next element is also A, so this A I will be pushing onto the stack. So if the second element is also A and topmost element is A, I will push that A also onto the stack. So this first step is common. What we did in the previous problem also is the same. We're just going on pushing all the A's onto the stack. Okay, so after pushing the second A in this figure, the pointer will move to the next. Okay, the pointer will move to first B. Now in Q0 state, when the first B is encountered, that time I will check what is there on top of the stack. If there is a matching A for this B, it will be cancelled. Okay, it means B will be cancelled with just previous A that was inserted onto the stack, that is the topmost A. Okay, so A will be removed from the stack, and automata will make the transition from Q0 to Q1 state. So in Q0 state, when the first B is encountered, and suppose A is on top of the stack, I will cancel out that B with A. That means the A, topmost A will be popped out, and I will move to Q1 state. This is for the first B. Okay. Now after this operation, the pointer will move to the next B. Correct. Now when another B is encountered, I am going to again check in Q1 state what is there on top of the stack. Okay, if B is encountered in Q1, I will check what is there on top of the stack. If there is a matching A, then this B will be cancelled with the corresponding A. So B will be cancelled with A. That means the topmost A will be popped out, and you will remain in the same state Q1, and pointer will move to the next element. Okay, so in Q1 state, I will write the same thing. When another B is encountered, again suppose on top of the stack there is A, so there is a matching that is happening. A and B will be cancelled, and you will be pushing null inside. Pop operation. A will be popped out, null will be pushed inside. Now, after this step, what happens is all A's and B's are already cancelled out. Equal number of A's and B's are cancelled out. Now, when the first C is encountered in Q1 state, the A's and B's being equal, they must have been cancelled out by now. So there should not be anything remaining in the stack. So when the first C is encountered, definitely the stack will be empty. So you will perform no change operation. That means you are ignoring C and you are going to Q3 state. Agreed? And this Q3 state, I will make it as a final state. Okay, this Q3 state, I will make it as a final state. Fine. So when the first C is encountered, I will perform no change operation on the stack, and the pointer will move to the next, to the one place to the right, and I will be in Q3, which is the final state. Fine. Now in this example here, there was only one C, but suppose there were say 2 A's, 2 B's, and say 1, 2, 3, 4, 5, 6, some 6 C's. Okay, then you would have done this business of ignoring and doing nothing onto the stack and just moving the pointer to the right. You would have done this business for those many number of times. So that means when the first C is encountered and when the stack is empty, you have already reached here. Now if there are any more C's which are encountered, in Q3, you are going to do the same thing. You are going to ignore those many number of C's, do nothing, and you will remain in the final state only. Now you will ask me, sir, why you have reached Q3 by reading just the first C? Because in case 1, the moment first C is encountered, that time, if the stack turns out to be empty, then it simply means that so far A's and B's which have been encountered, they are equal. So the moment you reach the first C, and that time if stack is empty, there itself you can say that that string is accepted, because case 1 only ensures that A's should be equal to B's and C's can be any number of C's, right? So that's why on encountering the first C, I am doing nothing but I am going to the final state. Now there could be more C's also like this. So for every extra C that we get next, you will remain in the final state only, doing nothing, do nothing operation on the stack will be performed. So this is case 1, for case 1. Then for case 2. Okay, now what is case 2? Case 2 is slightly different. Here A's and B's were equal. Now case 2 means A's and C's should be equal. Okay, so the valid string, suppose the valid string that we are going to trace now is say, it's a AA B CC. Suppose the string is AA B C C. So this is the Q0 state, initial state. Okay. Now, so Q0 is my initial state. Now, for A's, whatever operation I did here, the same operation I'll do here. Okay. So in Q0 state, when the first A is encountered, what I will do, that time stack will be empty, I will just push that A onto the stack. When any more A's are encountered, I will just push those A's also onto the stack. So this is exactly same. I will remain in Q0 state. Okay, now when the first B is encountered, now what we are going to ensure in this case, in case 2 is that A's should be equal to C's. So in between any B's that come, we are going to ignore them. Correct? So just see this operation of ignoring B. Now in Q0 state, if any B is encountered, at that time definitely A will be on top of the stack, because all A's, only after all A's are exhausted, then B start. So when the first B is encountered, okay, A will be on top of the stack. What you do? You perform no change operation. You are ignoring that B. That means A which was on top of the stack, A still remains on top of the stack. Do nothing operation. Now any more B's that you, now in this example there is only one B, but there might be n number of B's in between A's and C's. We are to ensure that number of A's and number of C's are equal, and we are going to ignore B's. Do nothing. So for the first B also will remain here. For second, third, fourth, fifth, any number of B's that are encountered, that B will be ignored, and A which was on top of the stack, A still will remain on top of the stack. That's the meaning of it. Okay. So graphically to show you, okay, see here in Q0 state, when the first A is encountered, A will be pushed onto the stack. Then the pointer will move to the next A. That A also will be moved onto the stack. Now when the first B is encountered in Q0, B will be ignored. That means A which was on top of the stack, A will still remain on top of the stack. You are in Q0 only, and the pointer will move to the next element, that is C. And now your cancellation business starts. Now in Q0, when the first C is encountered and topmost element of the stack is A, C and A will be cancelled. So this C you are going to cancel it with the A. Okay, that means the topmost A will be popped out of the stack. And of course the pointer will move to the next C. Right? And by doing that, let's say from Q0 you go to Q1 state. Now any more number of C's that are encountered, if they have a matching A on top of the stack, each C will be cancelled with each A, and you will go on doing this remaining in Q1 state. So this C, okay, since A is on top of the stack, this is that A which is on top of the stack. So this C will be matched with the topmost element of the stack, which is actually this A. So C will be cancelled with A. That means the topmost element of the stack will be popped out, and you will remain in Q1 state only, and the pointer will move one place to the right. Now when the pointer moves one place to the right, there is nothing remaining to be read, no? So finally in Q1 state, when there is nothing remaining to be read, stack also turns out to be empty, you perform do nothing operation and you go to Q4 state, which will be the final state. Okay, so by the time you start from Q1 to Q4, it will ensure that A's have been cancelled out with equal number of C's, and we have ignored B's. So now finally, what is the required PDA? The required PDA is actually the combination of case 1 and case 2. Okay, so I will write now, I will combine these two cases. Therefore, the required PDA is first I will write case 1. So case 1 we were ignoring what? We were ignoring C's. Okay, so initially when the first A is encountered, what we used to do? If stack is empty, we push it onto the stack. Any more number of A's encountered, push those A's onto the stack. So then when the first B is encountered, from Q0 you move to Q1. When the first B is encountered, okay, A is on top of the stack, you do the cancellation, Q0 you move to Q1, correct? Any more number of B's that are encountered, cancel it out with A, remain in Q1. Any more number of B's encountered, cancel it with A, remain in Q1. I am just writing, copying the same thing. Finally when C is encountered, do nothing operation, go to Q3. Finally, when C is encountered and stack turns out to be empty, do nothing operation and you move to Q3 state, which is your final state. Any more number of C's encountered, you will repeat the same thing of ignoring and remaining in Q3. That's a final state. So this is your case 1. Now I am going to add case 2 to it. What is case 2? You see, in Q0 state, this same Q0, in Q0 state, these two transitions will be same as these two transitions. Now this is one extra transition. So in Q0, you can say when B is encountered, A is on top of the stack, then what will you do? Okay, B is encountered, A is on top of the stack, then you cancel out B with A. Sorry, you ignore that B, that means A will be still on top of the stack. Okay, then in Q0, I'm just copying this. When C is encountered, C will be replaced with A. When C is encountered, C will be cancelled out with matching A, and I will just say I go to Q4 state. Any more number of C's that I encountered, any more number of C's, this I have written, any more number of C's that I encountered, replace it with A, cancel it with A, push null. See, I have changed the name of the state. I am not writing it as Q1, I am writing it as Q4 because in both the cases the state name is same, so you might get confused. Only the initial state in both cases will be same. So I will just call this as Q4 and maybe this I can call it as Q5. Okay, then when there is nothing remaining to be read, Z0, you go to Q4. So I will write it here. When there is nothing remaining to be read, Z0, you go to Q4. So this is the final state. Fine. So this is the required push down automata. Now one thing you all should remember is why this is non-deterministic push down automata. You see, from state Q0 on the reading B, from state Q0, please note, on the reading B, irrespective of what is there on top of the stack, you move to Q1. And from that same state on the reading B, irrespective of what is there on top of the stack, on the reading B, you go to the same state Q0. So on the reading B, from Q0, you make two transitions. Okay, and that's why this particular PDA is a non-deterministic PDA. In my next lecture, I will tell you how PDA traces a string. Now in deterministic PDA, we have seen there is something called as instantaneous description, which helps you to trace the string. Whereas since this is a non-deterministic PDA, there is something called as computational tree that we are going to see in the next lecture. Thank you.